In this video, we're going to talk about how to describe the amplitude and period of sine and cosine functions. So the general form of trig equations we talked about in the last video. So remember, A tells you the amplitude of the function, so that's half the vertical distance from the maximum to the minimum. 2 pi over b tells you the period of the function, so that's the interval over which the function completes a full cycle. In this lesson, we're not really going to talk about phase shifts or vertical shifts, but I just included them so you know where those values come from in the trig equations. So here it says, what are the amplitude and period of y equals 5 over 4 cosine negative 2x? So we can see from this equation, we're given a value of a and we're given a value of b. Okay, so a is going to equal the amplitude. So we know that the amplitude is a, and that is equal to 5 over 4. Now we need to figure out the period. So the period is given by that formula, 2 pi over the absolute value of b. So in this case, b is negative 2, so this is going to be 2 pi over the absolute value of negative 2, which is 2 pi over 2, and that equals pi. Okay, so that's going to be the period of this function. So here it says the graph of a sine function is drawn. One full cycle goes from 0 to 2 pi over 7, and the lowest point on that cycle is located at pi over 14, negative 2. What function could represent this graph? So we know we have a sine function, right? So we know we're working with y equals a sine bx, right? Because in this lesson, we're really talking about amplitude and period. So I only need to include a and b. So it says one cycle goes from 0 to 2 pi over 7. Okay, so that's telling us basically the length of a period. So we know the period is 2 pi over b. Okay, so if that's equal to 2 pi over 7, we can pretty quickly figure out that b is equal to 7. Okay, and then it tells us that the lowest point is located at pi over 14 and negative 2. Okay, so if we think about the sine function, right? So the midline is at 0, right? At y equals 0, we have the midline of our function, and we know the amplitude can be the distance from the midline to the lowest point also, okay? So if we think about that, that's going to equal our y coordinate, right? This distance, because like since this is down here at pi over 14, negative 2, that distance in y is going to tell us the value of the amplitude. So what we can do is we can go ahead and plug that in. So we have y equals 2 sine 7x. Okay, and that could be a function that's represented by this graph. Because if you graph it in Desmos, it's going to have all these characteristics that it described. So what I just wanted you to remember is that the value of a, okay, what happens when we change a? Well, when we change a, here's the original function sine x, and when a gets bigger, okay, the graph gets taller, right? You see the distance from the midpoint, the midline to the maximum is bigger than it is in this original graph. When we make a smaller, the distance from the midline to the maximum is actually slower, okay? So it's like a shorter graph. Also, when a is negative, we have a reflection over the x-axis. When b changes, the period of the graph changes, okay? So that's why you see here, this is sine x, and you see this orange arrow showing us the period. It goes from 0 to 2 pi to complete one full cycle. When we put 2 in front of x, okay, we change the period to becoming pi because 2 pi over 2 is going to equal pi. So you see here, the period is shorter as indicated by this orange arrow right here. And then if we have sine 1/2 of x, the period is going to be longer. Okay, because if you do 2 pi and divide by 1/2, well, when you divide by 1/2, you multiply by the reciprocal, so the period is going to be 4 pi. So you can see it takes much longer to actually complete one full cycle. Also, when b is negative, you're going to have a reflection over the y-axis. Okay, so you can see these two graphs are kind of like mirror images of each other. Okay, so you'll see some questions where it asks you to match graphs to equations. Honestly, when you have this kind of problem, I really think your best idea is to go ahead and graph in Desmos. So for example, if I were going to solve this problem, I would just go ahead and pull up Desmos. And we want to go ahead and make sure our settings are correct, right? So you want to make sure and do x by pi over 2, and you want to make sure that y is set to 1, and you're also in radians mode. So I've already typed in these equations for a, b, c, and d. And so when I show you these graphs, okay, let's see if they match. So first of all, you want to look for key features, right? So we want to make sure that it has a y-intercept of 5 as shown here. And you see this graph, it's going to come down and then it's going to first cross the negative x-axis at negative pi over 2. But this one doesn't do that. It has this intercept right here at negative pi over 6. So we know that A is not going to work. Now let's try B. So B, you can see, has an intercept at 0, 0, and that's not what we have in this graph right here, right? This graph has the intercept at 0, 5. So you see how the intercepts can be a very good way for you to kind of match the graphs to the equation. Let's try 5 sine x. Okay, once again, same issue, right? 5 sine x is going to go through 0, 0. This graph does not go through 0, 0. Okay, now let's try the last choice, 5 cosine of x. This one's looking pretty good, right? So 5 cosine of x, we can see that it does have that y-intercept at 0, 5, just like in the graph we see in that question. It does have the y-intercept, the x-intercept at negative pi over 2, 0. It has the intercept over here at pi over 2, 0. And you can see all the other points really match up very nicely with the graph that's shown in the question. So that's how we can say it's answer choice D. So any graph that's like that, where you have to match a graph with an equation, I would honestly suggest using Desmos.